So I've reduced in age and gained a little bit of weight. Unfortunately, Andy couldn't be here today. I know a lot of you were probably looking forward to hearing his talk, but he broke his arm skiing. If only we could all ski so aggressively at that age. So I wanted to talk about 400 gig and 800 gig Ethernet and optics, especially in the context of how the internet will be built over the next couple of years. The first thing that we would note, oh, I thought I was on here, so I'm going to stay over here, I guess. The first thing that we would note is that there's a big transition that's about to happen. I think everybody's probably well aware of this at this point. The 400 gig Ethernet transition has begun. They're already shipping products with 400 gig. And people often ask, how do we get faster in the internet? And the first thing we could say is by just going faster. And this sounds a bit cheeky, but the point of it is to say that as new technology becomes available, we continue to increase the speed of interfaces, both on the electrical side and the optical side. And we want to increase the speed as much as we can vertically rather than horizontally, as long as we can track against Moore's law. The new technology learning curve cannot be such that it's dependent upon a significant amount of cost up front to be borne by early adopters. This isn't just a claim to make about technology in our space, but it's a claim to make about technology in all spaces. When you think about high volume early adopters, they're not going to buy into a new technology that costs more than the existing technology, especially at volume. The cost of that technology must be such that there's an advantage to move there. And that should be obvious, but it hasn't been, at least until recently, both with the rise of merchant silicon and the increase in capacity and the availability of advanced digital signal processing and other modulation advantages in the DSP level that allow for this type of enhancement and this type of acceleration of new technology at the appropriate price points. So when we think about what's happened over time, looking at 40 gig to 100 gig and then to 400 gig, we can see that the 40 gig ramp began in 2014. Well, that's at least when the technology became available en masse. 2015 was relatively light. And then by 2016, we had a pretty large amount of 40 gig. And then at that same time, 2016, the 100 gig capability came online. And it only took about a year for 100 gig to surpass 40 gig port shipments. And then now we're starting to see that accelerate even still. And then if you look at the bottom right of the chart here, you can see that in 2019 into 2020, we'll start to see 400 gig ramp up. But note that 100 gig capacity and 100 gig port counts will still be very high. I think everybody's probably aware that 40 gig was a short-lived experiment, and we'll see why in a moment. If you look at it differently, you'll see the same thing. In this case, 20 million ports are estimated to be shipping by 2019 in terms of both 40 gig and 100 gig, but the vast majority of them are 100 gig. And this is because they're more cost effective. Right? It's more cost effective, it's more power efficient to use 100 gig than 40 gig. And the optical capacity, or the cable infrastructure, I should say, in most of the large data centers support a transition from 40 gig to 100 gig. And as we'll see, using the same cable infrastructure, the transition to 400 gig as well. Now, the 400 gig ramp in Ethernet ports for switches in data centers is expected to be somewhat less aggressive than the 100 gig ramp. And I'll explain why in a moment, especially the differentiation between the transponder-based long-haul optics and the data center non-transponder-based optics, or the short-reach optics. And that's largely because the systems are just coming online this year, and there's already there was such an aggressive ramp in 400 gig that, in 100 gig, that the 400 gig ramp will take a little bit longer, but we'll eventually get to a similar point. You can see here that over the course of 3 years, we go from less than less than a million 400 gig ports. And then by 2022, we'll see up to 10 million ports or more that'll be shipping. But by then, as you'll soon find out, we'll be looking at 800 gig. And of course, the reasons: qualification, new systems, and new optics available. 400 gig optics will likely start to become available. They're already sampling now. Most of the vendors out there have 400 gig samples in their labs and in their testing environments. 400 gig optics will be shipping this year. 400 gig systems are already shipping, but not all of the systems. So this is the time for this type of inflection to take place. Now, the vast majority of 400 gig will take place in the cloud, and this is kind of expected. I mean, there are, I think, more than 10 million, upwards of 20 million, I should say, but 10 million cloud data center ports, 100 gig ports in deployment at this point. It's probably more towards 15 million. That's an estimate. Of course, nobody knows exactly how many there are. So you can see that the vast preponderance of deployments will be in the cloud. The rest of cloud, it also includes service providers. And then, of course, the large enterprises are the ones that are shown in the pink here. So, cloud will represent almost 90 or more % of the total 400 gig shipments over the next 4 years, as expected. So this indicates a couple of things. One, where is the volume and spend? And where is the technology going to be focused around that will drive this volume of spend? Because the volume and the highest volume of spend will then, of course, drive the prices down and get you the most bang for your buck if you pursue a particular technology. And what I'm going to get to, is you'll see, is that we're at the precipice of being able to do both client-side optics or data center style optics and long-haul coherent optics in the same footprint, in the same pluggable, at the same power envelope, or at least within a power envelope that is supported in a typical system. One last point here on the crossover point, which is, I think, probably key for some people's thinking about when they should engage. If you know, we're still deploying 400 gig in mass, and the amount of total bandwidth shipped in terabits, again, multiplied by 1,000. So we're at 4.4 million terabits of capacity shipped eventually at 2020. At this point, around 2019, we're about half that, about 2 million terabits per second of capacity shipped. And that's kind of where you sort of see it flattening off at 100 gig while the 400 gig ramps. And then by 2020, that's where we think that 400 gig will surpass the shipments of 100 gig. And that's about the same time that we'll start to investigate the 800 gig path that will come next. Now, in order to get to 800 gig, we need to get beyond 50 gigabits per second SerDes. And 50 gig SerDes are just becoming available now on NPUs and on ASICs, which is really the way we want to drive the optical systems directly, because we want to have effectively a one-to-one capacity between electrical lanes from the chip and the optical lanes on the fiber. This avoids us from having to deal with gearboxes, which are power hungry, consume power, of course, and are costly. So if you can see, this is a bit blurry. I'm not sure why this came out this way. The orange portion of the graph is 10 gigabit SerDes. That was the technology of choice for some time. Then more recently, 25 gig SerDes came online in 2015 and will continue to be used for some time. 50 gig SerDes are coming online in 2018 and 19. This changes the optical modulation that we'll see on the lines on the optical lanes themselves that will drive new standards in terms of optical technology, and it will have some impact on interoperability. We'll talk about that in a moment. But the 100 gig SerDes transition happens around 2020 to 2021. And this is where we start to get into the 800 gig range with the same modulation techniques and the same number of lanes as we have in place for both 100 gig and 400 gig. So you're going to see that we're moving from this sort of 100 gig, 400 gig, 800 gig, not by coming up with more advanced or more exotic modulation schemes, but simply by increasing the lane speed. And that's the key when we say the best way and the fastest way to go faster is to go faster. Now, merchant silicon has grown at the same pace, and this, if you look at this pace here, you can see we're at the point now we're at 2x every 2 years, which is Moore's law. So as long as we're tracking along Moore's law and we're increasing the capacity of merchant silicon, this indicates to us that we need to increase the capacity of the optical lanes themselves. It means if we're going to double 2 times every 2 years, we should increase the capacity of the optical system about that rate, or 4 times every 4 years, which is where we are today. And another example here is with the current Jericho 2 chip from Jericho 1 Plus from Broadcom. 5 times the capacity over 2 years is a significant leap. The same thing is similar on the Tomahawk family, except it's more like 2 times every 2 years. So we're getting to this point where in order for us to continue to grow the internet, whether it's in the data center or the data center interconnect, we have to track along Moore's law. We have to take advantage of these speed transitions, both in SerDes technology as well as in chip speeds or in processing capacity. Now, I just want to briefly touch on the data center optics, because I think this is the part that we see the volume, or at least a good portion of the volume. So therefore, this gives us a bit of an idea of what the economies will be driven by. I know that Christian, before I'm the other Christian, by the way, he spoke a bit about data center optics, so I'm going to try to make sure that we don't overlap too much. So there are a bunch of standards. Everybody's aware. I'm more of a networking guy. I think most of the people here who know me wouldn't necessarily consider me to be an optics person. I see a 400 gig interface and it's 400 gigabits per second, and I'm happy with it. But there are a lot of different standards for a lot of different reasons and for a lot of different uses. And of course, one of the biggest use or drivers behind the different standards is the cost of the capacity, the cost of the fiber, and the cost of the optical technology. So effectively, we're trying to find a sweet spot between distance, cost, and the cable technology that we're using. And of course, in some cases, the splicing requirements or the cost of splicing. So we have these different types of fibers. If you note here, different types of fibers, different types of optical schemes, and different reaches and modulations. Each one of these, as you'll see in a moment, is an evolution using the same infrastructure and effectively the same technology, just 4 times faster as its previous generation. So for example, and this is a picture from Microsoft, if you look at the whole data center and ask yourself, where do you see 400 gig fitting, given the technology that's in place today and the capacity and the fibers that are deployed, it's everywhere. So it starts down at the TOR or at the server level with, currently today we have 100 gig CR4 copper optics. We can go to 400 gig CR8 copper optics in the same distance for the most part. At the leaf layer, then we go from like 100 gig active optical cables to 400 gig active optical cables, the same technology there. Then as you go up towards the spine layer, then you go from like 100 gig CWDM4 to 100 gig FR4, 400 gig FR4, I should say, or 100 gig parallel single mode fiber to 400 gig DR4. And that 400 gig DR4, of course, and the FR4 can be broken out into 100 gig DR and 100 gig FR. So we have the same technology available to us as we go, and the same thing for LR4. For 100 gig DCO, for long haul, the next standard that's coming from the OIF is called 400 gig ZR, and that's going to be the focus of my talk for the remainder, because this is where we finally get to the ability to have an optical component that's pluggable, standards-based, interoperable across multiple vendors, ultra-long reach. And what we're talking about here, just as a prelude, is imagine 1,000 kilometers coherent technology in 20 watts envelope, unrepeated. So this is the technology that we're talking about for the future. And so I wanted to talk about this at length. So what is 100 gig ZR and ZR Plus? As I mentioned, it's the first multi-vendor DWDM standard, standardized through the OIF. So, traditionally this long-haul business is the domain of the optical vendors, the line-side system vendors, or the line system vendors. And so there's a lot of proprietary technology there, a lot of high-power technology. Certainly some advanced physics are at play in some of these ultra-long-haul systems and some of these line systems. But it's been a boon to the vendors, the optical vendors, and it's been a bane, if you will, to the operators, because the operators then don't really have the same freedom and flexibility that you have, as with what you have in the case of Ethernet, for example, in routers and switches that you can either buy commercially or through an ODM or whatever it may be. They're coherent, tunable, pluggable. So this is a big deal as well, because now if you have the right packaging, you can take a pluggable optic, or at least a package, a port and a switch, and plug a short reach data center optic in, and pull it out and plug a ultra long reach or a long reach coherent optic to drive across a metro or even across a country, as I'll show you in a moment. 400 gig, 300, 200, and 100 gig speeds. So this is, of course, the distance bandwidth product. We can play around with this based on the Shannon limit and what we have available on the fiber. And because it's so dense and because the power is so low, the next generation optical modules for 400 gig, the OSFP and QSFP DD standards, allow up to 36 ports per one rack unit. So you'd say to yourself, well, that's great, but if I can't cool the thing, or if I have to alternate or checkerboard the optics because the capacity of the system, the power is not available, for example, or the heat dissipation is risky, then you don't get the full capacity of the system, so you don't get the savings that you'd want. But in our case, and this is something that's easily demonstrable, we can plug in, for example, 36 ZR Plus optics at 20 watts per optic and drive that system. We've done all the simulations and actually done whatever testing we could do with existing samples. We can drive that technology at the capacity, the thermal capacity of the system without any major issue. The only issue, of course, becomes things like NEBs, where once you're at that kind of heat capacity or heat dissipation and that type of power on the system, then it's questionable how much power and how much heat you can dissipate by spinning fans at certain decibel levels, right? You have acoustic noise issues and things like this. But for non-NEBS applications or for environments where you can avoid some of the acoustic noise challenges with NEBS, then you can envision a system like a modular chassis, something with 16 slots in it, 36 ports of 400 gig ZR optics or ZR plus optics, driving all of them long distance. Now, of course, that would be an unusual configuration unless it was like a mega core router in the middle of the ocean or something like that. But you certainly can envision the worst case scenario, and that's something capacity that we support today. And it's a 20-watt power envelope. I don't want to get into too much of the debate between QSFP-DD and OSFP, but 20 watts is higher, and that will allow us to go to ZR plus, and we think in the future will get us to 800 gig ZR when we have 100 gig MSA, 100 gig SerDes on the next generation systems that'll come out in 2021. Now, there's a huge cost reduction at play here as a result of this new technology. Because the optics are plugged, well, first let me try to explain this chart because it's a bit multidimensional. So on the left we have shipments in thousands. On the right we have the cost in thousands per port. And on the bottom there's the total number of shipments for both 100 gig, 200, and 300 and 400 gig optics, or 250 and 3 and 400. And you can see that the average sales price for 100 gig has been, of course, dropping over time, starting in 2012 at about $90,000 per port, and now it's down to about $20,000 per port. And this is for traditional packaged optics. So this would be something like a CFP. And the same thing for 200 gig for CFP2 or CPACs, or in the previous case as well. And then 400 gig with CFP8, as an example. This is the cost of a sort of packaged optic without the pluggable nature that you get with the economies of scale that you get in data center optics. But with economies of scale in ZR with OSFP or QSFP-DD, let's just use OSFP for now, we get down to about $10 per gigabit per second. So that's an order of magnitude reduction in cost for the same capacity in the network with the density that you'd expect to find in a large-scale dense system that you would put in a data center. Now, there's a lot of standards in reach. I don't want to go through all of them here. This is a bit of an eye chart, but what we have is, the typical client interfaces, 400 gig, 2 by 200 gig, 4 by 100 gig, or OTU4. The framing, we'll go through the whole list of them here, but a typical ITU framings or OIF framings, the ZR1 is, for example, is one of them. IEEE 802.3CK is one you'll find widely used. Open ROADM stuff that's starting to come out in some of the long-haul applications. Modulation schemes are ones that we all know and love, mostly QAM and QPSK for the long-haul stuff especially. And then the reach, and this is the big one if you notice here, and I don't know if everybody can read this in the back, but the reach goes from 100 kilometers for 400 gig at 16 QAM to up to 8,000 kilometers at 100 gig QPSK. This is on a single optic that's about the size of the size of a kazoo or something like that. It's about the size of a, what is the size of an optic? So this is amazing, right? You don't need a transponder anymore. You just need of course you need a MUX, but you don't need a transponder to drive a signal across an ocean at 100 gig. So this is, I think, going to have a big impact in network designs for service providers and for operators who are building long-haul networks. So as an example, some use cases for DCI, that's an obvious one. We're seeing more and more even sort of the metro DCI, where we have data centers in metros, and the leaf spine topologies are spanning the data centers. So it's not just like an aggregation layer or some ring between data centers. It's actually the leaf spine ECMP fan out is going, you might have some spines in one data center and leaves spread through multiple data centers, and those links are going up into this this data center that's in a different location across these DCI interfaces. Same thing with Metro Reach DWDM. We're starting, obviously a lot of ring technologies out there today for Metro. One of the things that we see examples of is ring technology that leverages segment routing with TILFA, so that you can do effectively zero-touch provisioning. So you can, imagine a ring that's about 100 kilometers in diameter. There'll typically be one long, sort of stretch, especially depending on how it's being built. But typically there's, a starting point, and then you start to touch a couple of different nodes, buildings, or whatever they are, and then you go around a big loop, and that end of the loop is typically a very long reach loop. So you need to have something that can go maybe 80 or 100 kilometers. You also need to be able to break the ring open and put it back together and insert new nodes and dynamically reprovision. So this is another use case that we think is going to be quite interesting. Of course, long reach DWDM. I'll show you a couple examples in a moment because that's exciting. And then 5G aggregation in R5 for cable. Obviously, this is something that's big and top of mind for everybody. 5G purports, and depending on who you believe and what kind of soothsayer you trust, could potentially increase the capacity over the next 5 to 10 years by 60x. And that's not just the 5G itself, it's the applications that it enables. So if you're talking about something like AR and VR, which are the ones that really look to drive the technology, that requires intrinsically requires a mobile interface if it's going to be useful. Now, the way everything's been done to date is the mobile interface, your phone acts effectively like a Wi-Fi hotspot, or maybe a 4G hotspot is a better way of saying it. But more and more, these devices are going to become connected themselves. So this is the Internet of Things. And with 5G, that bandwidth will increase. So if you have some kind of AR glasses, they may not be connected to your phone anymore. They're connected directly. So that's another example. Now, I mentioned that DWDM long haul is one potential application. So here's an example of the Internet 200 gig research network. It's a proposed network. I don't think this has been done yet. But if you just look at the map, and if anybody here is roughly familiar with US geography, you can see there may be only 1 or 2 places in the whole network, particularly the Trans-Montana, North Dakota, Bozeman to Fargo link, is probably the only link that exceeds 1,000 kilometers here, modulo 1 or 2 others. And in those cases, you could put repeaters, or maybe you just put another node somewhere in the middle. I don't know where in that case you would do it, Sioux Falls or something like that. And then the rest of the links are just direct shots. So you just plug the optic in, plug it into the MUX, forget about the transponder, it's already built in, and you drive it across the long distance. Now, I'd also note that those optics are standard-based, so it's an OIF standard, so you can get them from multiple vendors. So the lock-in that you used to have on the long haul, where one side had to be the same as the other, at least on the line side, is gone. Likewise, the case with Europe. In fact, all of Europe can be covered if you count, or if you exclude some of the farther reaches in northern Scandinavia. All of Europe can be covered by 400 gig ZR plus, because all the distances between all the major cities is less than 1,000 kilometers. So here's an example of a pan-European network that can be built using this technology without any DWDM or ROADM-based transponders. And the same thing goes for Asia. So across most of Japan, the ASEAN region, the southern Southeast Asian region that you see in the C block over there, and then the D block itself, with the exception of some of the links between Australia and New Zealand and the farther reaches in the northern part of the Pacific, and of course across the Pacific towards North America and South America, all of those links subsea can be covered by this technology. And if it's not 400 gig at 1,000 kilometers, it could be tuned down to 300 gig at 2,000 kilometers, or 200 gig at 4,000 kilometers, or 100 gig at 8,000 kilometers. So you can parallelize the links. If we always have to deal with this Shannon limit and the Nyquist concerns that we have with distance and bandwidth, as we know, signal-noise ratio be damned. But these are the things that we can do now with this new technology. So why the pluggable form factor? There is, I think everybody here who spends any time looking at optics knows that there's onboard optics technology that's being proposed that would increase the density, obviously increases performance and efficiency, but you lose the ability and the flexibility of being able to go pluggable. The most important reason why customers want modular, well, there's a couple of reasons. One of them is to avoid margin stacking, which is where you have multiple players in the food chain who are all taking a bit of margin. And this was the case, for example, with the CFP technology, and that's why the cost that we're showing for ZR plus optics is so dramatically different than the cost of existing CFP8 technology. So CFP8 technology, I think I referenced something like $10,000 a port, whereas the cost for ZR plus can be as low as $1,000 a port, let's say. A system vendor can build one system design. This is about per optic, by the way, and this is at volume. A system vendor can build one system design, so there's no extra investment required to deliver this DCO technology. You don't need a separate line system or a transponder shelf or whatever it is. It's literally one component. So all the system vendors, the merchant vendors, the custom vendors, the ODMs, the white box vendors can all leverage the same technology. You can mix and match DCO and client optics. This is probably the biggest one. It's certainly big for data centers, but networks are being built in a scale-out way. So it's not just routers that do this and routers that do that, and then switches over here, and then leaf switches and spine switches. They're all starting to blend together in a horizontally scaled fashion. So you'll see more and more that you'll have switches deployed in data centers that are leaves that have client optics towards the spines, and then have a mix of client optics towards local servers or local attach, especially in the telco space. But then you may have some, like for example, imagine a data center that's built inside a central office, like a mech data center. You could have some local attached servers, and then you might have some longer reach optics that go into subtending central offices or out to RFI hubs and nodes, or out to 5G backhaul sites. So you're going to need this flexibility, and you don't want to have to buy a co-packaged co-packaged line card with co-packaged optics that only have one specific style or type, because you lose flexibility. And then there's a lot of different SKUs that we can expect as a result of what I mentioned before, all these different types of considerations around distance and cost and the fiber type and what you're evolving to, and all these other concerns that people who build big data centers have. So the transition, as I mentioned, we think that'll go towards OSFP and QSFP-DD. I think Arista, it should be clear, although we have, as a company, been proponents of OSFP because we see the value of being able to transition forward to 800 gig and to support the higher power envelope that we can find in an OSFP module. We also support QSFP-DD. So the roadmap to 800 gig ZR, this is an important one because I think people ask right now, I think there was a bit of a debate whether it was going to go from 400 gig to 1T. I think that debate is largely settled. There are 1T capable systems. I think they're largely proprietary on the line side. The OAF meeting that's occurring right now in Arizona, I think, and I don't want to be the first to break the news, but I think that the larger agreement is that 800 gig will be the next speed transition. And if that's the case, then we have the technology available to us right away by just increasing the lane speed and the SerDes capacity from 56 gigabits per second to 112, or from 50 to 100. Same power envelope for 100 gig ZR. The longer haul will be something that we have to check and see how that'll work, but at least ZR optics, 800 gig ZR will work within the existing OSFP power envelope. So that means you can get 800 gig at less than, about 100 kilometers, probably a couple of 100 kilometers based on enhancements and perhaps some technological advantages, or advances, I should say, that some of the vendors are making to the DSPs. But it's possible to be able to build a network today with existing technology, the technology that's coming out now, using OSFP or QSFP, but particularly OSFP, and then be able to transition directly to 800 gig when the technology arrives. Just to summarize on the ZR Plus piece, because this is the real key here, it's the first true multi-vendor interoperable DCO standard. There was some 100 gig sort of standard floated. I think Peter Lothberg and some others put something together with staircase spec, and it had some traction, but it's not quite the same thing as having a full-on OIF spec. So this is a multi-vendor interoperable standard. It's been tested, it's been demonstrated at ECOC and at OFC. OFC is in 2 weeks. You can go there and check it out again. The revolutionary price performance is just unmatched. To be able to get down under a couple of $1,000s per 10 gigabits at this point is just revolutionary. You're thinking, I'm sorry, for 400 gig. It's so different. I mean, we're looking at the potential to have ZR optics at 400 gig at a couple of $1,000s depending on your volume. And this is like now, like this year, not next year and the year after. Low power, so this means you can really pack in a line card a lot of capacity. If you think about the NPU, the power that, so imagine a one rack unit line card or one rack unit system. How much power does it need to, and how much power can you put in a rack? Well, it's 20 watts for the optics and you get 36 ports, that's 720 watts. Then the NPU is going to be 500 watts or thereabouts, between 300 and 500 watts, depending how many there are, for example. So, when you add everything together, the fans, the connections, the CPU, the NPUs, the optics, and you're at about 2,000 watts per slot. And if you imagine, or per rack unit, so that gets you about 88,000 watts per rack, approximately. So this is starting to stretch the capacity of cooling technology today, but it is possible. I mean, it's only 88,000 watts. Anybody up for liquid cooling at this point? Pluggable form factor, eliminates a separate transport shelf. This is something that people have wanted for a long time, but this is really the real deal here because it's not just the metro, it's the long haul at this point as well. No special, of course, system designs where you have to have special dispersion compensators and things of that nature in the network. to do the DCO aspects. And I think we can definitely get to ZR plus 800 gig in 2022, 2023 timeframe. So this is investment protection. I think whatever investment people are going to make over the next couple of years, especially in the next 2 years in their systems, because there's a lot of next generation system technology available today, and we know that these typically last for many years and sometimes as much as a decade. This is probably the right direction to go in our view in order to meet the capacity requirements of the future. So I think I'm going to finish here. There's just a couple more points I wanted to make. This is stuff that you already know. This is the octal small pluggable form factor. So it's 8 by 100 gig SerDes in the future. So you can get 28.8 T per unit in this, up to 20 watts. I mentioned this already. QSFP-DD, I think you guys have seen this as well. 14.4 units per terabit, because it's not clear yet that QSFP-DD can support 800 gig, just because of the thermal characteristics of the system. Another piece here in terms of what we think is better about OSFP, I won't spend too much time here because we're not really taking a religious stance here, just an explanation of technology. This is a 112 gig PAM4 demonstration of SerDes. You can see the drift here, the signal drift, and it's hard to read that line there, but the spacing we get there, 25 decibels signal noise ratio at 28 gigahertz, gives us like sort of a demonstrable proof that we can do 112 gig on the existing technology. So when we have chipsets, for example, NPUs that can do 100 gig SerDes, we'll be ready to plug these into these OSFP form factor optics. This is pretty much the same thing I've been talking about in terms of 20 watt capacity. And then this is the same thing going from 400 gig. There's not, at least today, based on the estimates, there's not a significant change in the power requirements, or at least a savings in power, but there will still be savings in the system, because to go from 400 gig to 800 gig, it's half the lasers, it's double the density. So even if we can't get a huge power savings based on what we know about the technology today, we think we still can get a system-wide savings, because we know we can get a system-wide savings because we'll get advances in switching performance, in ASIC performance, and of course, the reduction in lasers. So the biggest challenge for operators is to figure out how to increase bandwidth for the next-gen applications without increasing CapEx and OpEx. In fact, we'd like to lower them. And I think the key is to, the first thing that Arista has done, and I think a lot of people in the industry recognize this, is look at merchant silicon as a way to step into this space with reduced cost of R&D, where we get a common set of technology that everybody can use at a commodity price. And then, of course, reducing the cost of DWDM and long-haul optics. So for service providers and operators who operate long-haul networks, this is the second half of that, or the second side of that coin. The first side of the coin of reduction cost, in our view, is merchant silicon. The second side is, of course, these high-speed, long-reach optics that are pluggable. It's easier to manage. Everybody knows this, right? This is an issue with ECMP. In one case, a lot of more ports to configure, a lot more optics to provision. So the faster capacity that we can get, the higher the speed, the easier it is to manage. And it's lower cost. So 400 gig today, just so to be clear, even if you're not ready for 400 gig today, 400 gig technology is half the cost per bit. It's half the power per bit, double the capacity. 4 times the capacity for the existing systems. So it makes sense to move to this technology, even if you're not fully ready to go 400 gig or you don't have the capacity requirements. So it's something to consider when you're starting to look at your new systems. So there's a huge improvement in bandwidth and price performance. This is key, I think, especially if we want to reduce cost. Fundamentally, more cost-effective networks are also more efficient and easy to manage. So I think this is a fundamental precept that I think operators are starting to embrace more and more. And we think that we'll have trials and production of 400 gig this year. It's certainly in data centers, and then long haul, we'll start to see that come online late this year and early next year. And that's it. Any questions? Thank you.
Wes George with ByteGrid. Apparently it's my day to talk at NANOG.
Hey Wes, good to see you.
Since you've mentioned in a number of different places in your talk the challenges around power and cooling, wanted to mention something that it's come up in previous discussions we've had with router vendors about this exact problem. Give some thought to NEBS extended specifically. Mm-hmm. There are an awful lot of applications where NEBS extended compliance, like we don't actually need the box to keep running in those temperature ranges. And given the significant increase in power required to drive fans fast enough to keep it cool at those temperatures, having a mode where I can essentially say, turn yourself off if you get to this temperature. Thermal shutdown and derate the power requirements accordingly. There's a lot of places where that would be pretty useful. Yeah, there are going to be some places where people say, no, I want this box to run until it catches fire because this stuff is critical and it has to keep running. But there are also lots of places where that really isn't true. And so that may be something, you know, as this becomes more and more of an issue in terms of the power requirements on the individual packages, it might be something to think about.
Yeah, I think that was more of a comment, but if I can respond, and one thing I would say is, you know, that technology exists today to have different fan speeds. We find that, in fact, we've had the situation where we had a NEBS concern on acoustic noise, lower the fan speeds, but then they have a cooling failure. So then, you know, the system shuts itself down because, you know, we can't spin the fans louder, or we can spin them faster, and louder. But then that would violate the NEBS rules, right? So it's a tricky one. I think that the system vendor, the only thing I was going to say, the major response I was going to make is, and this is self-serving, so I'll preface it with that. Be careful what you wish for when you go after some of the ODM-based white boxes, because they typically aren't engineered for that type of flexibility. So if you care about that and you're looking at white box, just check how they behave under different power stresses and under different environmental conditions. Yes?
I was wondering about the on the server side, if there's any concern or if you're tracking the rates for the buses for being able to put in cards and what they can support.
So you're talking about like PCI 4, and I haven't looked at it personally recently, but if you want, just shoot me a mail and I'll get you in touch with the right people who know that stuff really well. I know exactly what you're talking about. I think the last I heard, I don't even think it's part of Ice Lake yet. Let's assume it is, but that would be now, this year, and I think the transition was still some time, so I'm not clear on it, but I'll check.
Thanks.
Yep. One more?
Hi, Paul Pittenger, Telstra.
Hi, Paul.
I'm imagining that this technology is even more demanding than ever on fiber quality, connector click, gap space to the lasers, all that. So are the vendors doing special test and implementation modes to help you hook this all up, and what role do these low-level transceivers play in that?
That's a good question. I don't have the answers for all the different optical types or all the different connectors, but the goal is to be able to enable this to work with existing plant. So that means that, you know, the existing MPO cables, the existing single mode fiber, you know, OM3, OM4, each one's different. I think at least in the data center case, the fiber is new enough and clean enough within the past, let's say 5 years, or let's say maybe even 10 years, to support this technology all the way up to 800 gig. But for outside plant, that's a different story, and of course, your mileage will vary. So I wish I could tell a better story, but I mean, some of the fiber in the ground is 30 years old or more, right? Looks like that's it. Well, hey, everybody, thank you very much for staying late. I know many of you wanted to see Andy, but he couldn't be here, so thanks.